All right, so today we're starting a lesson on graphing rational functions. In order to graph rational functions, we're going to need 6 pieces of information that we discussed yesterday. And those 6 pieces of information, what I usually call the 6 deadly sins or rationals, are as follows: the vertical asymptotes, the horizontal asymptotes, the y-intercepts, the x-intercepts, and the domain and range. Knowing those 6 pieces of information, I can then start making educated guesses of what my rational graph is actually going to look like. And so I want to walk us through how to actually find these 6 pieces of information from this graph f of x equals 1 over x plus 3. And based on the information I gather, I will be able to graph this on my graph back here and thus end the problem. So the very first piece of information that I actually need is the vertical asymptotes. And if you remember, the vertical asymptotes are found by finding the zeros of the denominator. So I'm going to look at my denominator. And my denominator in this function itself is x plus 3. If I want to find the zeros, I'm asking what x, when I plug it in to x plus 3, simplifies to 0. In this case, it is x equals negative 3. That is my only vertical asymptote for this problem. I go to the horizontal asymptote. Now, to actually talk about the horizontal asymptote, we're talking about the degree in the numerator and the degree in the denominator. Looking at my numerator, since there is no x in that, I know my degree is 0. If there's no x's in the actual polynomial, my degree is always going to be 0. Looking at the denominator, there is just an x. It's not x squared, x cubed, x to the fourth. It's just 1x. Since that would be x to the first power, my degree for the denominator is 1. And using our horizontal asymptote rules from yesterday, knowing that the degree of the top is less than the degree of the bottom, that tells us that our horizontal asymptote is y equals 0. Next, we need our y-intercept. What the y-intercept is going to allow us to do is be able to graph an actual point on the graph, which will tell us kind of where some of our curvature is happening. Our y-intercept is found by just solving for f of 0. And so over here, I'll go ahead and solve for f of 0. F of 0 is equal to 1 over 0 plus 3. So I am substituting in x, or 0 into x to give me 1 over 0 plus 3. Simplifying gives me the fraction 1/3. And I'll keep this as a fraction because fractions are much more exact than decimals. Writing 0.33 is a terrible approximation of 1/3, so I'll keep it as 1/3. So my y-intercept, and as we discussed yesterday, is a coordinate point. It's not just a number. I'll write this in coordinate point form, which is 0, 1/3. My x-intercept for this rational function is the zeros of the numerator. But because, again, there is no x in the numerator, we cannot have a 0 of the numerator because there's nothing we can plug into. Thus, if there is no x, there is no zeros of the numerator, which means there are no x-intercepts. So I will write just none. Of course, what this means graphically is that these graphs cannot cross the x-axis. And that makes a lot of sense when we discuss that our horizontal asymptote is at y equals 0. Lastly, the domain and range, we'll put it in the form of a set notation. And our domain for this rational function, x, contained in the set of all real numbers, except x cannot equal negative 3. Range, again in set notation, y is contained in the set of all real numbers, except y cannot equal 0. And from this, we can now have, hopefully, enough information in order to graph this. And so what I'm going to do now is I'm going to take all 6 pieces of information, and I'm going to put these on a graph. I want to start off with first my vertical asymptote. With my vertical asymptote, it is creating a line at x equals negative 3. So I'll go to the x-axis, I'll look for negative 3, and I will create a vertical line. And I'll draw this with just a dotted line. Next is my horizontal asymptotes. With my horizontal, I just got one at y equals 0. That is a horizontal line, and I'll just draw this again with a dotted line. And what this is going to do is it's going to constrain your function. Your function, the actual lines on your function cannot pass through these asymptotes for this particular function. And so what we need to do now is kind of look at the parent function of rationals to get an idea of what the curvature is going to look like. So I'll go ahead and just kind of below, I'll draw the parent function for this. Our parent function has that type of curvature, and so we hope that our actual function that we're graphing is going to have something similar. Now, the next point in order to determine if it actually is going to look like that, we need to go ahead and graph the y-intercept. The y-intercept was at 0, 1/3, which approximately would happen about right here. There is no x-intercept. We cannot graph domain and range, and so we have graphed everything that we can. Now, what this y-intercept has told me is that there is a curvature that occurs above this horizontal or this asymptote and to the right of this vertical asymptote. And so I can go ahead and draw a curvature right there. That passes through the y-intercepts and is bounded by those asymptotes. So it can never actually cross the asymptotes. It's constricted inside there, and that y-intercept tells me it is up there. And then the next step, the very final step, we need to figure out where that curvature is going to occur. If it's going to occur either up top or if it's going to occur on the bottom. Now you know it cannot occur over to the right and below, because if there was a curvature down here, this would create something that's not a function. If you do the vertical line test with a curvature down here, you would find that it is 2 points and thus not a function. So the only two possible places are here and here. So this is where I introduce what I call a test point. So I'll go ahead and draw another piece of information down here, test point. And all we're going to do is we're going to choose a point that's somewhere to the left of the vertical asymptote and see if it's above the x-axis or below the x-axis, or in other words, see if it's positive or negative. If it's positive, I'll know I can draw a curvature that's bounded by the asymptotes above. If it's negative, I'll draw a curvature that's bounded by the asymptotes below. And so I went ahead and choose something easy. The integer that's to the left, my vertical asymptote, is at -3. So I'll choose -4 as the one I want to try. So I'm going to find f of -4. I'll substitute a -4 into x. And from the looks like this, it looks like it's going to be negative, because my bottom part simplifies down to -1. And when you divide 1 divided by -1, you are left with -1. So my test point of -4 gave me a result of -1, which means that there is a curve below the x-axis, and I can now draw it. So we have now, using the 6 pieces of information we found before, graphed this rational function. This is a rational function that we graphed with only one vertical asymptote, which tends to be a little bit easier. Usually the y or x-intercepts will tell you where the first curve goes, and then you would just need to figure out a test point to find out where the second curve goes.